Hello everyone, welcome to this video. Today we are going to explore limits at infinity. First, we are going to define limit at infinity. If the function y equal to f of x approaches to a finite number L as x approaches to a large positive number or large negative number, then we call it limit at infinity. And mathematically, we write this as limit as x approaches to positive or negative infinity of f of x equal to L. So if I want to represent this graphically, here I have the graph of the function y equal to f of x. So this is my graph, y equal to f of x. And as you can see here, when x becomes larger and larger, this graph approaches closer and closer to this horizontal line, whose equation is y equal to L. Y equal to L. So meaning of that is when the value of x approaches to positive infinity, when the value of x becomes large and it's positive, this function approaches to the function value of L. Similarly, on the right hand side, if you look at it, when the value of x approaches to negative infinity, this function first increases and then it decreases and it gets closer and closer to the value y equal to L again. That means on the left, when limit as x approaches to negative infinity, the limit is L. And also on the right, when limit as x approaches to infinity, that's positive infinity, it's L. So when you are looking at the extreme limit as x approaches to negative infinity or x approaches to positive infinity, we call that as limit at infinity. And if the limit at infinity is equal to a finite value, so this value, the limit is finite. Maybe here the limit is, here is 20, here is 40, maybe this value is like 35 or 37. So maybe this y is equal to 37. So that is a finite number. So if the limit at infinity approaches to a finite number, then we say that this horizontal line, if you look at this horizontal line, the graph approaches closer and closer to that horizontal line. Meaning of that is the horizontal line will be the asymptote. So if you are asked to find the equation of the horizontal asymptote, we calculate the limit at infinity. And if it is equal to a finite number L, then we say that the line y equal to L is horizontal asymptote of the function y equal to f of x. So that is the fundamental idea about limits at infinity. Now let's look at some examples. Calculate the following limits. Here in these three examples, we have to find the limit as x approaches to infinity or negative infinity. Let's begin with the first part, A. In part A, we are asked to find the limit as x approaches to negative infinity of 5 plus 7 over x squared. So when I say x approaches to negative infinity, it's a negative number and it's very large negative number. Okay, it's very large negative number. So when I say very large, I'm talking about the magnitude. So here is 0, negative infinity will be here. So this one is like negative 999999999, just like that. Very big, but negative number. Magnitude wise, it's very big, but it's a negative number. Now here, we are squaring that negative number. When you look at it, here is x squared. So when you square that negative number, it's going to be positive, and very large positive number. When you divide 7 by very large positive number, when you divide a finite number by very large number, the result will be 0. So this will be 0, and that's 5. So the result will be 5 plus 0, which is equal to 5. So the limit is 5. Limit as x approaches to negative 5, negative infinity of 5 plus 7 over x squared is equal to 5. That is the limit for part A. Now let's work on part B. In part B, we have to find the limit as x approaches to infinity of 7 plus sine x over the square root of x. Now, if you try direct substitution here, we don't know exactly how much is sine infinity. When I say positive infinity, it is over there, a very big positive number. When you go closer and closer to that big number, when the value of x is increasing, your sine x is still fluctuating between 0 and 1 like this, because the value of sine is between 0 and 1. So we cannot exactly determine the value of sine. So because we will not be able to exactly determine the value of sine, we cannot perform direct substitution. Instead, we have to use a different technique to find this limit. So what I'm going to do is, in order to compute this limit, I am going to use a squeeze theorem. What I know, let me begin with the known fact. What I know is your sine x is between -1 and +1. Sine x is between -1 and +1. So from trigonometry, we know this one. But if you look at the expression here, we have sine x divided by square root of x. So now I'm going to divide throughout by square root of x. So this implies -1 over square root of x is less than or equal to sine x over square root of x, which is less than or equal to 1 over square root of x. Still, the function here is not the question that is asked here. It is 7 plus sine x over x. That means I need to add 7 here. So in order to add 7 here, I have to add 7 here and also here. So let's add 7 throughout. So this will be 7, then minus 1 over the square root of x, less than or equal to 7 plus, that is positive, so plus sine x over the square root of x is less than or equal to 7 plus 1 over the square root of x. So now this function, 7 plus sine x over x, is squeezed between 7 minus 1 over square root of x and 7 plus 1 over the square root of x. Now what we are going to do is, we are going to find the limit as x approaches to infinity of 7 minus 1 over square root of x and 7 plus 1 over square root of x. So let's try that. Now, limit as x approaches to infinity of 7 minus 1 over square root of x. That will be equal to, if we examine this carefully, this is a large number. So 1 divided by large number is very small, approximately 0. So this is 7 minus 0. 7 minus 0, which is equal to 0. So this limit on the left end, which is 7 minus 1 over the square root of x, that is 0. Let's find the limit of this one. Limit as x approaches to infinity of 7 plus 1 over the square root of x. That is equal to, so when x goes to infinity, when x is very large, when x approaches to a very large positive number, 1 over very large positive number is very, very small, approximately 0. So this limit will be 7 plus 0, which is equal to 7. I mean, 7 plus 0, that's equal to 7. Here, I made a mistake there. That is 7 minus 0, which is equal to 7. So we can see the limit of this function is 7. Limit of that function is 7. That means the limit of the function which is squeezed in between must be 7 by squeeze theorem. So let's write the conclusion. By squeeze theorem, the limit as x approaches to infinity of 7 plus sine x over the square root of x is also equal to 7. So in order to compute this limit here, we used squeeze theorem. So that is the limit for part B. Now let's find the limit in part C. Here we have to evaluate the limit as x approaches to negative infinity of 12x cubed plus 4x squared minus 7 all divided by the square root of 36x to the 6 minus 5x to the 4 plus 12. So let's work on this one. Okay, here, before we begin, we need to note one thing. This is the key concept that we'll be using here. The square root of x squared. If you try to recall the definition of square root of x squared, the square root of x squared is equal to absolute value of x. Square root of x squared is equal to absolute value of x, and this is equal to negative x if x is less than 0 and positive x if x is greater than or equal to 0. Square root of x squared is absolute value of x. That is the definition of square root of x squared. And the definition of absolute value of x is this. So that means square root of x squared is negative if x is negative, and square root of x squared is positive if x is positive or 0. That's why we say that the square root is positive or negative depending on where the x is. Now for this example, for part C, we'll make use of square root of x to the 6. So if we use the same definition here, when I say square root of x to the 6, that will be absolute value of x cubed. The square root of x squared is absolute value of x. Similarly, square root of x raised to 6 is x cubed, which is equal to negative x cubed if x is negative and positive x cubed if x is positive or 0. So we'll be using that concept here. Now, before we exactly calculate this one, if you look at this function here, you have the numerator and denominator, and in the denominator we have the square root. So in order to find the limit of function like this, we have to divide both numerator and denominator by the highest power of x in the denominator. So to evaluate the limit, let's now work on that part. Now the limit as x approaches to negative infinity. When x approaches to negative infinity, meaning of that is here your x is negative. Now what we are going to do is we are going to divide both numerator and denominator. Here in the denominator we have square root. So we are going to divide both numerator and denominator by square root of x raised to 6, because inside the square root there is x raised to 6. We divide both numerator and denominator by the highest power of x in the denominator. The highest power of x in the denominator is x raised to 6. So we are going to divide both numerator and denominator by x raised to 6. But keep in mind here that the x is negative because x approaches to negative. So square root of x raised to 6 is negative x cubed. So in the numerator, we are dividing by negative x cubed. So if we divide that by negative x cubed, this will be 12 x cubed divided by negative x cubed, which is negative 12. When you divide this by negative, it will be negative 4 over x cubed. 4x squared over x cubed is 4 over x. And then here is a negative. You are dividing by a negative, so it will be positive 7. You are dividing by x to the third, so 7 over x cubed. So all this is happening in the numerator without a square root. If there is no square root, it is negative x cubed when x is negative. But inside the square root, just divide by x to the 6 and you are good. So inside the square root, let's divide by x to the 6. When you divide this by x to the 6, it will be 36x to the 6 over x to the 6, which is 36. Then you have minus, you have 5. Then x to the 4 divided by x to the 6 is x squared. Then plus 12 over, you are dividing by x to the 6. So now we are ready to evaluate the limit. If we do this, we can find the limit by direct substitution. So this is equal to negative 12, then minus. Now when you divide by x, x is very big number. We already take care of that sign. So now we are just looking at that x. It's negative infinity. It's a negative number, but it's very big number, negative 9999999 like that. So this x is very, very large. When you divide 4 by very large number, that is approximately 0. Then plus 7 over the cube of large number, that's very large. So when you divide 7 by very large number, that is approximately 0. Then in the denominator, we have the square root of 36 minus 5 over the square of very large number, so that is also approximately 0. Then plus 12 over a big number raised to power 6, that is also approximately 0. So what we get here is negative 12 in the numerator, and in the denominator is square root of 36, which is 6. That means we get negative 12 divided by 6, that is negative 2. So that is the limit for part C. Example, describe the end behavior or describe the end for each of the following function. When I say end for each of the following function, I mean describe the end behavior for each of these functions. So the end behavior is same as the limit at infinity. End behavior, let's write this down. End behavior is limit as x approaches to positive or negative infinity of the function. So whenever we are asked to define the end behavior, we have to calculate the limit at infinity. So the first one is a polynomial function. To describe the end behavior of the polynomial function, we find the limit as x approaches to plus or minus infinity of 3x cubed minus 7x squared plus 12. One very important thing to note, whenever we are calculating or whenever we want to find the end behavior of polynomial function, this is a polynomial function, the end behavior of the polynomial function is just given by the leading term. So you can write this equivalently as the limit as x approaches to plus or minus infinity of 3x cubed. So it is just given by the leading term. Now we are looking at the limit as x approaches to positive infinity and negative infinity. So there are two cases here. Your first case is limit as x approaches to positive infinity of 3x cubed. And the other one is limit as x approaches to negative infinity of 3x cubed. Now, if you observe these two carefully, the first one is you're plugging in positive number, okay, very large positive number, and you are cubing it. Cube of a positive is a positive, a very, very large positive number multiplied by 3, that is still very large positive number. So infinity. On the other side here, when you plug in negative infinity, meaning of that is you are plugging in very, very small, I mean very, very large, but a negative number. Meaning of that is I'm plugging in number like negative 9999999 and so on. So when you cube that, that's also a negative, and that is very large in magnitude. You multiply by 3, your result is also negative infinity. So what we see here is the end behavior. When you want to describe the end behavior, if you think of the graph towards the left end, when I say negative infinity, that is towards the left end, the graph goes to negative infinity. That is the meaning of that. And then towards the right end, when x approaches to positive infinity, the value of the function is also infinity. Meaning of that is the right end of the graph will go up. So that is the end behavior of this function. This is a cubic function, so there are two turning points. So this should be the shape of the graph. Now you can see here, the shape of the graph matches with the shape of the graph that you have discussed in college algebra using the end behavior. So the left end of the graph goes down and the right end of the graph goes up. So we can easily describe the end behavior of the graph by calculating the limit as x approaches to positive or negative infinity for the given function. In B, we have to calculate the limit as x approaches to positive or negative infinity of 5x minus 7 over x squared minus 4. So whenever you are calculating the limit of the rational function like this, we have to divide both numerator and denominator by the highest power of x in the denominator. So this one will be limit as x approaches to positive or negative infinity. So highest power of x in the denominator is x squared. Now when I divide this by x squared, it will be 5 over x. Then minus, if you divide 7 by x squared, it will be 7 over x squared. And then when you divide this x squared by x squared, that is 1. And minus, when you divide this 4 by x squared, it will be 4 over x squared. Now let's find out what we'll get. So this will be equal to, now if you look at this carefully, when you plug in a very big, okay, either a positive or negative number, you are dividing 5 by a large number. Whether it's positive or negative, that will go to 0. Similarly, this one, 7 over square of that large number, infinity squared, that will be 0. Similarly, this one will also be 0. So we'll get 5 minus 7 over x squared. So 7 divided by a large number, that is approximately 0. The first one is also 0. 5 divided by 0. So 5 divided by x, 5 divided by a big number. Okay, 5 divided by very big number, that is 0, 0, 1 minus 0, which is equal to 0 divided by 1, which is equal to 0. So we got limit as x approaches to plus or minus infinity of 5x minus 7 over x squared minus 4 is equal to 0. Now let's try to understand the meaning of this limit here. So if we sketch the graph of the function y equal to 5x minus 7 over x squared minus 4, your graph will look like this. We can verify this using TI-84 calculator. Now you can see here when x approaches to positive infinity, when x becomes positive infinity, or when x goes to positive infinity, you can see that this graph decreases and it gets closer and closer to y-axis. Closer and closer to x-axis. So the value of y will be 0. So x-axis, the value of y will be 0. So it becomes 0 when you go to infinity. Similarly, when x approaches to negative infinity, when you go towards negative infinity, this graph increases and gets closer and closer to y equal to 0 because it approaches closer and closer to x-axis. So that is the meaning of that. We are looking at the end, the left end over here, the extreme left end and extreme right end. So towards the end, the graph goes closer and closer to 0. This will also tell you that when x goes to positive infinity or x goes to negative infinity, we are getting the equation of the horizontal asymptote. In this case, we have a horizontal asymptote y equal to 0. So you can write horizontal asymptote your horizontal asymptote is y equal to 0. So the equation of the horizontal asymptote is y equal to 0 because it is getting closer and closer to x-axis. So now note that the end behavior of the function will help you to find the equation of the horizontal asymptote. So end behavior, you can add this. End behavior gives equation of horizontal asymptote. Horizontal asymptote. That is very important thing that we must know. The end behavior of the function will give you the equation of horizontal asymptote. So that is part B. Now let's work on part C. In part C, we have to find the limit as x approaches to positive or negative infinity, because we are calculating we are looking at the end behavior. So we have to find the limit as x approaches to positive infinity and also negative infinity of the function which is given here of 8x to the 4, 8x raised to 4 minus 5x squared plus 1 over 2x to the 4 plus 3x squared minus 7. This is equal to limit as x approaches to positive or negative infinity. So this is also a rational function. So we divide both numerator and denominator by the highest power of x in the denominator. The highest power of x in the denominator is x to the 4. So we are going to divide throughout by x to the 4. If we divide 8x to the 4 by x to the 4, that will be 8. Then minus 5x squared divided by x to the 4, that is 5 over x squared. Then plus 1 divided by x to the 4, which is 1 over x to the 4. Divide that by 2x to the 4 divided by x to the 4, 2. Then plus 3x squared divided by x to the 4 is 3 over x squared. And then negative 7, we are dividing by x to the 4. So negative 7 over x to the 4. When x approaches to positive or negative infinity, 5 over x squared, 1 over x to the 4, 3 over x squared, and negative 7 over x squared, all of them will be approximately 0. So what we'll get is 8 minus 0 plus 0 divided by 2 plus 0 minus 0, which is equal to 8 over 2 or 4. So we get the limit as x approaches to positive or negative infinity as 4. So meaning of that is, if we want to see the horizontal asymptote, the equation of the horizontal asymptote is y equal to 4. So let me write that. So equation of horizontal asymptote is y equal to 4. We can verify this by graphing this function given here. If we sketch the graph of this function, our graph will be like this. This is just the sketch. We can verify this using TI-84 calculator. Now you can clearly see when x approaches to positive infinity, when x increases and becomes very, very large, you can see that this graph approaches closer and closer to that line y equal to 4. Similarly, when x approaches to negative infinity, this graph gets closer and closer to the same line y equal to 4. That's why y equal to 4 is the horizontal asymptote. Now part D. So to find the end behavior, here also we'll calculate the limit as x approaches to positive or negative infinity of 3x squared plus 5x plus 6 over x plus 3. Now, in order to find the limit as x approaches to positive or negative infinity of rational function. Now part D, we have to find the limit as x approaches to positive or negative infinity of 3x squared plus 5x plus 6 over x plus 3. So here also, because this is a rational function, in order to find the limit as x approaches to positive or negative infinity, we have to divide both numerator and denominator by highest power of x in the denominator, or x with highest power in the denominator, which is just x. So we are going to divide throughout by x. So if we do that, let's see what we get. This is equal to the limit as x approaches to plus or minus infinity. So we are dividing by x, so that will be 3x plus 5 plus 6 over x divided by, in the denominator, when I divide by x, that's 1 plus 3 over x. Now, you know that when x approaches to infinity, that will be 0. this will be 0. So that will be infinity. So what I'm getting here is this is equal to 3 times your x is positive or negative infinity plus 5, that is 0, 6 over infinity is 0, plus 1 plus 0. So 3 times plus or minus infinity, 3 multiplied to a very big number, that's also infinity, plus or minus infinity, plus or minus infinity, plus 5. When you add 0, that's just that. When you divide by 1, that's what you'll get. So if it is a positive infinity plus 5, positive infinity plus 5, it is positive infinity. Very large number plus 5. That's very large. And a very small number, or this is a large number with negative magnitude, plus 5, that will still be negative infinity. So here, unlike part B and C, in this one, when you try to calculate the limit as x approaches to positive or negative infinity, we are not getting a finite number. We are not getting a finite number. If that was a finite number, then y equal to that number is the horizontal asymptote. In this case, we didn't get a finite number. So meaning of that is there is no horizontal asymptote. So for this one, there is no horizontal asymptote. Let me write that. There is no horizontal asymptote. We can also verify this by drawing the graph of this function. So this is the graph of this function. So we can clearly see when you go to negative infinity or positive infinity, it's not going to any finite value. You can see when x goes to negative infinity, this graph is going towards the positive infinity. And also on this side, it's going towards positive infinity. So clearly, this graph does not have any horizontal asymptote. Now we have some idea on finding the equation of the horizontal asymptote. So let's try to find the equation of horizontal asymptote for these two functions here. Let's begin with part A. So we know that in order to find the equation of horizontal asymptote, we have to find the limit as x approaches to positive or negative infinity. So here, for the first part A, the limit as x approaches to positive or negative infinity of, we have 8x cubed minus 5 over the square root of 9x squared plus 3 plus 4x cubed. So if you look at this one, this is also a rational function. It involves a radical there, and here is x cubed. So when we divide both numerator and denominator by x cubed, here you can divide by x cubed, here you can divide by x cubed, here you can divide by x cubed, but inside the square root you cannot divide by x cubed. Instead, you should know something here. Your x cubed is same as square root of x to the 6. So meaning of that is, when you divide inside the square root, you have to divide by x to the 6, because x cubed is same as x to the 6 over there. So let's divide throughout by x cubed and see what we get. So this will be limit as x approaches to positive or negative infinity. So 8x cubed divided by x cubed, when you divide that, that is equal to 8. Then minus 5 over x cubed. In the denominator, you have the square root of 9x squared divided by x cubed, which is same as dividing by x to the 6. So this is 9x squared divided by x to the 6, which is 9 over x to the 4. 9 over x to the 4 plus this 3 is also inside the square root, so it will be 3 over x raised to 6. 3 over x raised to 6. Then plus, this is outside the square root. Outside the square root, you divide by x cubed. So 4x cubed over x cubed, that is 4. Now when x goes to positive or negative infinity, you can clearly see when x goes to positive or negative infinity, this will be 0, this one will be 0, and this one will also be 0. That means you'll get 8 over 4. Or let me write here, it will be 8 minus 5 over x cubed. That will be 0 divided by square root of 0 plus 0 outside the square root, it's 4. So this is same as 8 divided by 4, which is equal to 2. So meaning of that is the equation of horizontal asymptote is y equal to 2. So we can write equation of horizontal asymptote is y equal to 2. So that's how we can find the equation of horizontal asymptote. Whenever we are asked to find the equation of horizontal asymptote, we have to find the limit as x approaches to positive or negative infinity. Now let's work on part B. We have to find the equation of horizontal asymptote to the graph of this function. So we have the limit as x approaches to positive or negative infinity of x squared minus 9 over x squared minus 3x. So here, the highest power of x in the denominator is this one, x squared. So we are going to divide throughout by x squared. So this will be equal to the limit as x approaches to positive or negative infinity, x squared over x squared, that's 1, minus 9 divided by x squared over 1 minus 3x over x squared, that is 3 over x. When x approaches to positive or negative infinity, this one, 9 over x squared and 3 over x will be both approximately 0. So it will be 1 minus 0 over 1 minus 0, which is same as 1 over 1 or 1. So the equation of horizontal asymptote is y equal to 1. So let's write that. So equation of horizontal asymptote is y equal to 1. So that is the end of this video. Thank you so much for watching.